Welcome to this next part. In this part, we are going to look at fluid-fluid reactions in which reactants are there in two different phases. It could be liquid and another liquid, one in aqueous phase, one in organic phase. It could be gas and liquid, one reactant in the gas phase, one reactant in the liquid phase, and reaction is happening in one of the phases. And we are going to first of all look at how do we characterize these reactions, how do we quantify rates, how do we calculate rates, what are the various issues, and then we'll solve some problems, and then we'll see how to measure how to measure kinetics of such kinds of reactions. And finally we will look at some industrial applications or industrial reactors, and we can design some of them. So this is where we are in our course. We are on lecture 17, and in terms of the course, we are on the last part of our course, fluid reactions, mass transfer, because we are going to have two phases, two reactants which are reacting. We are going to have them in different phases. That's why, and reaction is happening in only one of the phase. That's why one of the substances or one of the reactant has to go from one phase into another phase. So mass transfer is required. So we have to think about mass transfer along with chemical reaction. Just like we had diffusion along with chemical reaction in a catalyst particle. Now instead of diffusion, we are going to have mass transfer into one of the phases, say liquid phase, and chemical reaction. Okay, we are going to look at all these things. Just to help you to revise, these are the things that we have done up to the last class. In the last part of the syllabus, I want you to derive an expression for concentration profile for pore diffusion limited first order reaction in a slab. What is the significance of Thiele modulus? Derive an expression for effectiveness factor. Write expressions for maximum temperature rise across the particle and across the film. If you answer these questions, automatically your revision of the previous lectures will be done, so that you are ready for listening to this lecture. Okay, so some general things that we are going to say. Let's say, for example, a gas liquid reaction. Although we are not going to be limited to gas liquid reactions, this is very often we encounter. In a gas liquid reaction, we have one reactant in the gas phase. We are going to call that as A. This is a generalized nomenclature we are going to keep for all other lectures henceforth. The liquid phase reactant we are going to call as B. The stoichiometry between A and B we are going to denote by a stoichiometric coefficient Z. So our reaction is going to be A plus ZB giving product. So for just to give you an example, for example, we might be having a reaction of paraxylene oxidation. So paraxylene oxidation giving us terephthalic acid, COOH. Let me write it properly. COOH plus water. Okay, so this is going to be our reactant A. This is going to be our reactant B. Now if you balance this reaction, we will need two water molecules, right? 6 hydrogen atoms, 2 hydrogen atoms, and 4 more hydrogens. So 6 hydrogen atoms. One oxygen molecule, second oxygen molecule, third oxygen molecule, right? We are going to write it as A plus ZB. That means we are going to divide throughout by 3. This is going to be 1/3, this is going to be 1/3, and this is going to be 2/3. So our Z is going to be 1/3. A plus Z times B. What does the stoichiometry mean? That if 1 mole of A reacts, if 1 mole of oxygen reacts, 1/3 mole of B reacts. That's the meaning of the stoichiometric coefficient. So if Ra is the rate of reaction, Ra is the rate of reaction of A, rate of reaction of B is Z times Ra. That's what we mean, Z times Ra. Okay. That's the meaning of stoichiometry. Okay. We are going to say this reaction takes place in the liquid phase. For the reaction to take place in the liquid phase, this A has to come in the contact with B in the liquid phase. That will happen only if A dissolves in the liquid as per its solubility. And now the reaction is occurring between dissolved A and B. So if you want to write rates of reaction Ra and Rb, we are going to say Ra and Rb are point rates of reaction, kilomole per second per meter cube, and V is the volume of dispersion. If this is our reactor, if this is our reactor, if this is our reactor, we are going to say gas flow rate multiplied by concentration of A coming in, gas flow rate multiplied by concentration of A going out, liquid flow rate multiplied by concentration of B coming in, liquid flow rate multiplied by concentration of B going out. So kilomoles of B reacted would be QL into B in minus B out multiplied by, so this would be equal to in minus out must be equal to amount that is reacted. So that's nothing but rate of reaction per unit volume for B into dV. This is to be integrated over this whole control volume because RB can be different at different locations. We will see as we go along how to do all these things. Same way for A, QG multiplied by A in minus A out would be integral of RA over dV, and RA and RB are related to each other. In other words, we can write that QL into B in minus B out would be Z times QG into A in minus A out. So this variation of RA and RB in the reactor depends on whether it is well mixed or not, whether it is plug flow or not, which means it depends on the flow behavior or RTD. Now you see how RTD is coming into picture. If the reactor is well mixed, RA and RB are the same at all locations in the reactor. Whether it is here, 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 anywhere you go, RA and RB are the same. Right? Then just integral just becomes RB into V, RA into V. Right? Let's go forward. What we are going to do now is to write the steps involved in the reaction. Can you write them? Pause and write. Here are some. So first of all, diffusion of a reactant through the gas film. Now A, which is in the gas phase, could have some mass transfer resistance in the gas phase itself. So there is a mass transfer resistance of A from the bulk gas to the interface. There could be dissolution of A in the liquid phase. After this A is transferred, it has to dissolve in the liquid phase. We are going to denote solubility of A by A star. Once it is dissolved, then A can start reacting. Then A will diffuse inside from the interface to the bulk of the liquid and then react. We are going to denote dissolved concentration of A in the bulk of liquid as A naught. And we are going to denote concentration of B in the liquid bulk as B naught. So then diffusion of reactant occurs through this liquid film, reactant A, and then it reacts. Okay. I want you to draw qualitative profiles of A and B. Draw. Pause the video and draw to explain this mechanism. Okay. Draw for yourself. Here is how it is going to look like. So imagine this is our reactor. Let's look at the vicinity of one bubble. Okay, if this is, let's say we are in the vicinity of this bubble. What is it going to look like? It's going to look something like this. Let's go further and let's zoom in on any one of the bubble, right? Let's say this bubble, for example. Now what we can see, we will see this blue bubble phase, that is the gas phase, and we will see this yellow liquid phase. This is our interface between the bubble and the liquid, gas and the liquid. On the left side there is a gas film, on the right side there is a liquid film. There is a gas bulk and there is a liquid bulk. So if you want to draw concentration profiles of A, concentration would be constant in the bulk. Then there is a mass transfer resistance for A. Then there is a dissolution equilibrium between the A in the gas phase and A in the liquid phase. This we are going to call as A star. Then there is a diffusion and reaction of A. with B, because A is there, B is there in the liquid. This concentration is now we are going to call as A naught, dissolved concentration of A in the bulk. This dissolved concentration of B in the bulk of liquid we are going to call as B naught. And then as B is reacting here, there could be diffusion of B from the bulk to the liquid film. But we are not going to write diffusion of B in the gas side, because we are going to say B is non-volatile. So B does not go to the gas side. Otherwise reaction would start happening in the gas side also. Indeed it does happen when you have nitric oxide absorption to make nitric acid. Some water goes in the vapor phase because of vapor pressure. Then the reactions between nitric oxide and water happen in the gas phase, as well as reaction between nitric oxide and water happen in the liquid phase as well. Okay, so these kinds of things happen. Right now for our course we are going to say that B is non-volatile, so B does not go in the gas phase. Okay. If you have understood, then go forward, otherwise spend some time understanding all these. Suppose I assume gas side mass transfer is negligible, gas side mass transfer resistance is negligible, and we assume that consumption of B in the liquid film is negligible. Then concentration of A would be like this, and concentration of B would be like this. Now draw concentration profiles of A naught in the liquid phase when rate of reaction of A is greater than the liquid side mass transfer of A, and rate of reaction of A is less than the rate of liquid side mass transfer of A. Draw here. Pause and draw. This is how we will get A in the gas side, it dissolves, so you will get A star, there is mass transfer, and then this is our A naught. Now if we increase the rate of reaction, what is going to happen? Or if we increase mass transfer rate, what is going to happen? These two conditions. Right? Let's write. If I increase mass transfer rate, this is what is going to happen to profile of A. Do you realize? Imagine that suppose you are here and there is A is the food. Okay? So if you are very hungry, means you react or you consume food at a very high rate, and food is coming from kitchen. There are two steps in series. Transfer of food from kitchen is like mass transfer of A, and your consumption of food is like reaction of A. If consumption of food is very fast as compared to its transfer from the kitchen, then as soon as the food comes, you have eaten it. Concentration of food on your table is 0. But if I increase mass transfer rate of the food as compared to the rate at which you consume, then food will accumulate on the table, and finally food will be saturated on the table. Table will be full, as if the liquid phase is saturated. So A naught would be equal to A star, and A naught would be equal to 0 here. Okay, do you understand? Think, comprehend all of this, then only we will go forward. Pause the video, comprehend, then only go forward. So we are going to quantify all of this. So let's say order of reaction with respect to A and B we denote by M and N, and let Kmn denote the rate constant for the reaction in the liquid phase, and let epsilon L denote the fraction of liquid holdup in the dispersion. Meaning, if this is a dispersion, if this is our dispersion, this yellow fraction of the liquid occupied in this dispersion, yellow fraction in this liquid dispersion is epsilon L. Gas fraction, the blue fraction, is epsilon G. Okay. Let's denote volumetric mass transfer coefficient per unit dispersion volume as KLA. So at steady state, now you see these two steps are in series: diffusion of A, mass transfer of A, and consumption of A. They are in series. So at steady state, we can write a balance RA would be epsilon L Kmn A naught raised to m, B naught raised to n. I write anywhere, let's say at this particular situation, it is A naught and it is B naught. Rate of reaction would be epsilon L, because rate is per unit volume of liquid. Reaction is happening only in the liquid. Epsilon L Kmn A naught raised to m, B naught raised to n. And this, because they are in series, this must also be equal to KLA into A star minus A naught. Mass transfer rate and reaction rate. As a simple situation, let's consider first order reaction with respect to A and B. So M and N are 1. So then RA becomes epsilon L K2. So M and N are 1. I should write K1 1, but we are writing K2. Overall second order, first order with respect to A, M is 1. First order with respect to N, B is 1. B naught, N is 1. Is epsilon L KLA A star minus A naught. A star I can measure from solubility. A naught we can't measure. I don't want to take a sample and analyze. So we can eliminate A naught, right? Then RA would be A star epsilon L K2 B naught, 1 by epsilon L K2 B naught, 1 by KLA. So 1 by KLA is like the mass transfer resistance. 1 by epsilon K2 B naught is like the kinetic resistance. And again, this is like resistances in series because these two steps are in series. Do you understand? Are you comfortable with this? If not, think and go forward. Only when you are comfortable, go forward. Comprehend, understand, analyze one slide completely. Once you are convinced, once you are understood everything, then only you go forward. So we can think of two extremes. Epsilon L K2 B naught is far less than KLA, means kinetic resistance is very large as compared to mass transfer resistance. Means kinetics are slow as compared to mass transfer, or very slow if you want. This extreme, epsilon L K2 B naught, is far greater than KLA, means mass transfer is slow as compared to kinetics. So rate expression would be epsilon L K2 A star. Now you see it is A star here into B naught. Why A star? Because it is all saturated. It is all saturated. A naught is equal to A star. This is called as regime 1. Denoted as very slow reaction. Very slow with respect to what? It is very slow with respect to mass transfer. That's why very slow. Okay. In general, for any M and N, epsilon L Kmn A star raised to M, B naught raised to N has to be far less than KLA into A star. For the other case, we call it as regime 2, slow reaction regime. In general, epsilon L Kmn A star raised to M, B naught raised to N is far greater than KLA, and RA would be KLA into A star. Why A star? Because reaction is fast, A naught is 0. So rate is KLA into A star minus A naught, and A naught is 0. Two regimes. Regime 1, very slow reaction. Regime 2, slow reaction. Regime 1, completely kinetically controlled. Regime 2, mass transfer controlled. If you want, we can call this as regime 1 rather than writing it as slow. The reason I am writing it as very slow is because in the textbooks it is written that way. But we should call this as completely kinetically controlled. Kinetics is rate determining. This is mass transfer control. All right, let's go forward. Imagine now, what if the mass transfer is happening, but what if I increase the rate of reaction further and further, higher than that in the regime 2? Equivalently, what I'm saying here is, now here the rate at which food comes and rate of consumption of food by you, they are in series. But what if you are very hungry, as if your reaction with food is so fast, you can't wait, by the time it is delivering from kitchen to here, mass transfer, you start eating it. You go to the interface and start eating the food by the time it gets to the table. That's how hungry you are. That's how hungry you are. So then diffusion and reaction will become parallel. They are no longer in series. If reaction rate goes up even more than this situation, then diffusion and reaction will start becoming parallel. Simultaneously it is diffusing and it is reacting. I want you to draw concentration profiles. So this is the case for regime 2. I want you to say now what happens to the concentration profile if I increase the rate of reaction further and further, Draw a profile, pause and draw for yourself, then only go forward. This is how it will look like. Reaction rate is increasing further. Did you see this before any time in any other lecture? Is this not like mass transfer and chemical reaction in a catalyst pellet, diffusion and reaction in a catalyst pellet? Yeah, it is. Yeah, it is. Are these in series or parallel? Now here they are in parallel. They start happening simultaneously. Identical situation as that of diffusion reaction in catalyst. Let's consider first order reaction with respect to A. Okay, so our pseudo first order rate constant is K is K1n V naught raised to n. It need not be first order with respect to n, but it's pseudo first order with respect to A, right? So we are saying this is how the concentration profile looks like. Let's make this dimensionless. A bar as A divided by A star, X bar as X by delta. Delta is the film thickness. Then this equation will apply. You see this? This is like Thiele modulus if we were talking about catalyst. Here L instead of delta, the mass transfer film thickness, it was L, half the thickness of the slab. Instead of A of diffusivity in the liquid, it was effective diffusivity through the catalyst pellet. Here we are not going to call it Thiele modulus. Here K delta square by dA we are going to write as Damkohler number. Another way of writing it is K delta square by dA. I can multiply and divide by dA. I will write it as dA K by diffusivity by delta. That's like mass transfer coefficient in the liquid side. That's easy for us to visualize. So it becomes dA K by KL square, and square root dA K by KL we call as Hatta number. Either we can denote it as HA, but let's denote in our case by dA K by KL square equal to M. Why M? Is because one of the textbooks calls it as M. Okay. So our equation now is d square A bar by dx bar square is equal to M A bar. Very similar to catalyst, right? At x bar equal to 0, A bar is 1. A by A star is 1. At x bar equal to 1, dA bar by dx bar is 0. I am taking the same boundary condition. We could have taken another boundary condition as well, that at x bar equal to 0, at x bar equal to 1, we could have also taken that A bar is equal to 0. Why? Because the reaction is fast. It has all got consumed before it has gone. But I am trying to write a generalized case. I am just trying to show you analogy with respect to the diffusion and reaction in the film. That's why I am taking this boundary condition. But actually I should be taking this boundary condition. We had the same expression. This equation and this equation and the boundary conditions are identical. That's why I am taking this as a boundary condition. That's why I'm taking this as a boundary condition, just to show you that they are identical. But further treatment is not identical. And our solution was, this was our solution. Ca bar was cos phi 1 minus x bar divided by cos phi. So now our phi is root m. See? So a bar would be cos root m 1 minus x bar, cos root m. And dA bar by dx bar at x equal to 0 is minus root m hyperbolic tan root m. So as before, our rate in terms of kilomoles per second would be flux multiplied by cross-sectional area. This was our cross-sectional area. See the previous slide. You would get this. Now instead of defining effectiveness, where in the catalyst pellet we said everywhere it was like A star everywhere, maximum possible when diffusion limitations are not there. Instead of defining in as an effectiveness factor, what we will say is what would have been the mass transfer rate in absence of physical reaction, in absence of reaction, which means if there was physical absorption occurring, how much A would have got absorbed, and then define something called as enhancement. So rate, this is from our previous slide. Okay. If no reaction occurs, then the total rate of absorption would be KL, S and A star. So now this dA by delta, that's our KL. This is our KL. S, A star. What is our flux? What is the extra term? This is our extra term. This is our extra term. So this term KL into A star, or if you want to write volumetric rate, KL A into A star, this term represents physical mass transfer. And this term tells you is a multiplication factor. Why this is coming? Because of rate of reaction, because kinetics are faster. That's why it is not a, so if it was physical mass transfer, you see it would have been like this. This is for physical mass transfer. This is actual. Isn't the rate higher, slope higher, dCA by dx higher in this case as compared to this case? So it is like enhancement. So this is like our enhancement due to chemical reaction. Enhancement due to chemical reaction. So this enhancement factor we can define as Ra divided by KLA star, which is root m multiplied by hyperbolic tan root m. And if root m is greater than 3, hyperbolic tan m is almost 1, tan root m is 1, enhancement factor is equal to root m. And then the rate we could write as root m multiplied by KLA and A star, enhancement factor. So rather than defining as effectiveness factor, as if we should actually define it as effectiveness factor. What would have been had mass transfer limitation not been there? Concentration everywhere would have been A star, and the rate would have been K M N A star raised to M B naught raised to N epsilon L, of course. But we are defining based on enhancement over physical mass transfer. Why we do that? Because this happens very often. We'll do a problem after in the next couple of lectures, is or maybe at the last, is people were trying to do physical absorption of gases, so carbon dioxide absorption in water, and if you add an alkali, carbon dioxide absorption increased tremendously in water. So that's why people defined it in terms of enhancement in mass transfer. Okay, that's why we define in this particular case as enhancement in mass transfer rather than writing effectiveness of reaction. So these are the two extreme things. These are the two extreme things. Diffusion and reaction is the same, whether it is catalyst pellet or whether it is in the liquid film. In catalyst, we say effectiveness of the reaction, whereas in fluid reactions, we are going to say enhancement in mass transfer. Just two different ways of looking at the same thing. If a glass is there, one way of saying if a glass is there containing 50% water, one way of saying is glass is half full. Other way of saying is glass is half empty. Half empty is like saying with respect to reaction, it could have had 100% filling, but it's half empty. Its effectiveness is only 50%. Other way is saying glass is half full. As compared to mass transfer, it has something more enhanced. These are the two different ways of looking at the same thing. Understand, realize this, then go forward. Okay. This is called as fast reaction regime. So what conditions need to be satisfied? Write for yourself, think and write for yourself, pause, then go forward. Okay, one is kinetics have to be faster, which means epsilon L K2 B naught has to be far greater than KLA, and root m has to be greater than 3. So root m is root dA K by KL. This has to be greater than 3. And then rate would be root m into KLA into A star. Homework: derive an expression for enhancement factor considering the boundary condition x equal to delta to be A equal to 0 rather than dA by dx equal to 0. So do this for yourself. Do this for yourself. I'm not going to do. Second, derive an expression for Ra and root m for a reaction of order m and n, generalized now. Try to do it yourself. Struggle, but do it yourself. Pause. Here is the answer. So if it's an order m and n, we can write dA d square A by dx square kmn A raised to m B naught raised to n. This is in the film, so A is the concentration. It's not A naught or A star. It is at any location, it is A. At any location, it is A. At this location, it is A. But it is B naught at this same location. B naught. We are neglecting resistance for transfer of B. Okay. So that's why A and B naught. Let dA by dx be psi. So then I can represent from here. Simplify. You will get this. You get this. Oops, sorry. You will get this expression. Total rate would be dA, S and psi at x equal to 0 minus. Okay. So rate would be minus dA A bar. So surface area now. This surface area, so it is now total rate, surface area per unit volume is our Ra. So it is S divided by volume. That's why it has become A bar. This is S divided by volume. Surface area per unit volume. Okay. Simplify. So this is our enhancement factor. See this derivation for yourself. Make sure you get yourself. And RA is KL will just cancel out. RA is A bar A star square root 2 by m plus 1 dA kmn A star raised to m minus 1 B naught raised to n. Do this for yourself. Check whether you get this for yourself. Let's go forward. Let's go forward. Sometimes you could have reaction between regime 1, 2 and 3, which means reaction is fast, that some A reacts in the film but not all. A naught is finite. Draw concentration profile. Pause. Draw for yourself. A naught is not 0. So what conditions need to be satisfied for this case? Derive an expression for RA for this particular case. Okay. This is homework. Okay. Now imagine that reaction is so fast that it consumes B at a very rapid rate, at a rate more rapid than the rate at which B can diffuse. So B naught cannot be now constant. If you do that, I wanted to draw concentration profiles with increasing rate constant. Do this. Okay. So now A diffuses and A reacts, and rate of reaction is so fast that the mass transfer of B is less than the consumption of B. Then B will also deplete. So depletion of B in the liquid film. Now increase it further, increase rate further, increase K further. Draw here, do for yourself. Pause. Further depletion. Increase K further, draw for yourself. Like this. Increase K further, draw for yourself. Look at this extreme case. This extreme case is like rate of reaction is so fast that A and B cannot exist together. Wherever A is there, B cannot exist because B will be completely consumed by A. Wherever B is there, A cannot exist because it will be completely consumed by the reaction. That's how the reaction is so fast. So fast. This last situation is called as instantaneous reaction. A and B cannot exist. They exist only here. They exist only here. Left side of this, there is mass transfer of A, but there is physical mass transfer of A because there is no B to react. On the right side of this, there is physical mass transfer of B. Physical because there is no A. A has been consumed before that. They come and consume each other instantaneously. Both A naught and B naught are 0 at this point. This location is called as reaction plane. As if the reaction is happening on this plane, nowhere else. Let's go forward. I want you to derive an expression for RA. Let's call this reaction plane. Let's say reaction plane is lambda from the interface. So this diffusion length of B is delta minus lambda. Okay, here is the answer. RA would be dA by delta into A bar A star minus 0. RA is per unit volume. That's why I'm multiplying by A bar. A star minus mass transfer of A. Same way, mass transfer of B, RB dB delta minus lambda A bar B naught minus 0. Then these zeros can be just neglected. And what is our RB? RB is Z times RA. So dB delta minus lambda B naught is equal to Z dA by lambda A star. So we can solve for lambda because lambda is unknown. So delta minus lambda by lambda would be dB B naught by Z dA A star, or delta would be delta by lambda would be 1 plus dB B naught by Z dA A star. So lambda by delta would be reciprocal of this. What is the situation? If dB B naught by Z dA A star is far greater than 1, that means this is very large, 1 is very small, neglect that, and lambda tends to 0. Means if B is very high, B naught is very high, diffusivity of B is very high, then this reaction plane is practically at this interface. As soon as AC comes at the interface, it is consumed, gone. If dA is very high, A star is very high, dB is low, B naught is low, then lambda is tending to delta. Means A diffuses, and instantaneously B is consumed at this edge of the liquid film. And we can substitute now for lambda here. You will get RA would be dA by delta, that's KLA A star, and 1 plus dB B naught by Z dA A star. This is now our enhancement factor. Okay. Understand, do it for yourself. This is called as regime 4, instantaneous reaction. So if you just try to summarize regime 1, very slow reaction, right? This is the condition, this is the rate expression, generalized for M and N. Regime 2, slow reaction, this is the expression. Regime 3, fast reaction, generalized expression. Regime 4, this is the rate expression, this is the condition, this is the rate expression. You try to understand all these things. When you say very slow, it is reaction is very slow compared to mass transfer. Slow means reaction is slow as compared to mass transfer. Fast means reaction is fast as compared to mass transfer. So there is depletion of A in the film. Instantaneous with respect to mass transfer of A and B. So reaction plane is formed. Otherwise, this very slow, fast, instantaneous has no meaning. They have a meaning because they are defining reaction rate as compared to mass transfer. We'll do a problem in the next class. Let's go a little further. So you could have, these are continuous. It's not as if there are distinct boundaries. You could have reaction between regime 1 and 2. This case. You have regime between 2 and 3. This case. You have between 1, 2 and 3. There's between 3 and 4 also. I'm just not writing that just now. Not very relevant just now. Okay. So understand all these things. Think about all the things that we have said so far. Comprehend. All the things that we have said, you can read in Levenspiegel's book, chapter 23. Or there is another book, Heterogeneous Reactions, Doraiswamy and Sharma, volume 2, chapter 2. All these things are denoted there. And this book, Doraiswamy Sharma's book, chapter 2, it defines, instead of defining it as Hatta number, it is defined in terms of M or root M. Here it is defined in terms of Hatta number. Okay. what we have done so far is do a framework, write a framework for fluid reactions, comparison between mass transfer and chemical reaction, mass transfer with chemical reaction. Okay. Now we can solve some problems based on all of this. That's coming in the next lecture. So we'll stop this lecture here.